I'd like to introduce you. His name, Professor Dr. Didier Pasquale. He's from University of Littoral Côte d'Opale, abbreviation ULCO, ULCO, French. The topic is functional materials and oxide for application. His research field, uh, first functional ceramic and thin films, electrical characterization, piezoelectric and ferroelectric properties, yeah. And then ferroelectric detectors, gas sensors, and SOFC, solid oxide fuel cell. Uh, he's also in collaboration with us, especially for my lab. He's become a co-promoter for Mr. Septian. Yeah, so I supervise with Dr. Bambang, Professor Bambang, and Professor Didier to supervise Mr. Septian. Fortunately, Septian every years, yeah, go to the France, yeah, with the Professor Didier to do some experiment. Thank you for this opportunity for Septian to do the research. So I would like to give this moment to Professor Didier to give his guest lecture, and he will talk about two, two topics. Yeah, yeah. And I think if you have a question, yeah, if you want to go to the France, for example, yeah, Professor Didi will help you, yeah, or maybe want to introduce you how to apply and how to, for example, uh, they get a scholarship or and so on. Yeah. So thank you, Professor Didir, and this guest lecture will be guided by Mr. Septian. Yeah. Thank you.
Thank you, Pak Budi. Now we are going to have the public lecture from Professor Didier. Okay, Professor Didier, the time is yours.
Cool. So I'm very happy to be with you today, and effectively, my main interest in research is for solid. What? This one is better. Yeah. So main interest is for functional oxides. Functional oxides are a huge family, and of course there are so many developments today for this kind of oxide, because here we are talking about the possibility to develop solid state devices, and all possibilities, we'll talk about that, are possible, and especially because this material, this oxide, can be composed of different other oxides, and of course it's possible to develop and to deposit them into different thickness. So from the bulk, which generally, has thickness, from half a millimeter to some millimeters, in function of the power you need. You can also develop some thick films, and also thick film means you have a thickness ranging from 10 to 100 micrometers generally. After that, you can decrease the scale, and you can deposit by different techniques. You have physical techniques, you have chemical techniques. You can deposit some thin films. Thin films in literature and scientific literature means that your material has a thickness, weaker or lower than 1 micrometer. So for the thickness of thin films, we are talking about nanometers, generally from 50 nanometers to 500 nanometers. So, and among, these huge possibilities of application of all these families of functional oxides. Here today, in the first part of my talk, I will speak about, the theoretical and computations for the optimization of the first study you can do to help you for choosing, some oxide or some doping to improve the properties of this oxide. That's why my first talk is optimization route of functional oxides from prediction to characterizations, because I will also talk about characterization. And here we need so many equipments to do all the physico-chemical characterizations to the electrical characterization for many applications. So after the introduction, I will talk about prediction to give you a definition of that. I have chosen, some special things because, of course, I'm the head of a group in my lab, so we do many things. And here I choose to talk about at first ceramics, and then about thin films, and with a theoretical aspect. Functional oxide, what does it mean? Functional oxide means you can do some functional application with this oxide. And here, this oxide have a wide range of interest functionalities. In particular, for many applications, they have high dielectric permittivity. The high dielectric permittivity is required, for instance, for capacitors. When you want to develop some capacitors for electronic application, electronic device, in your smartphone, you have a lot of these tiny capacitors, which are made with effectively oxides. So these oxides have also very interesting properties like piezoelectricity, pyroelectricity, and ferroelectricity. Piezoelectricity, we are talking about transducer and actuators. Pyroelectricity, we are talking about infrared sensors, for instance. Ferroelectricity, we are talking about the possibility to store an information. So currently, in our notebook and computers, we have FE-RAM, so ferroelectric random access memories. They are still in your computers. So other applications can be effectively ceramic capacitors dedicated to all kinds of frequency range, because you have low frequency dedicated to power supply, all power supply you use for every equipment, or up to, finally, high frequency range, because for telecommunication, of course, you function above 1 gigahertz. That's why you need special components, especially special capacitors, because your capacitors need to have very good properties, electrical properties, in this high frequency range. So we are talking about also tunable devices. When you have effectively electronic application, you need generally to tune something, for instance, a frequency for an oscillator. If you have something which function and which is generating a signal, you have to tune the frequency. That's why you need tunable devices. Actuators, we have currently, a lot of actuators using ceramics. Sonars. Sonars are one of the most well-known application of this functional piezoelectric functional oxide. Sonars means high power transmission. Then we have also infrared sensors. Infrared sensors are used for the detection of effectively warm bodies, whatever effectively the body, and then theoretic memories. So if I go deeper, into these materials, I am effectively talking about physical interaction and properties of these special materials. So we have various properties. We can effectively have different families of properties: electrical, mechanical, and thermal properties. After that, you can decline these properties to effectively sub-properties like dielectric, piezoelectric, pyroelectric, and thermoelastic. Another application means electrocaloric. Electrocaloric means effectively you can generate a thermal variation in function of a electric voltage. That's currently there is a heavy studies, for that in literature. If you type, on Google Scholar, if you tap this word, you will see tons of papers, because the idea is to replace effectively some fluids. Currently, we use fluids and gas, to generate cold temperature. Here, it's possible to do it, electronically, I would say. So converse piezoelectric is the reverse piezoelectric effect, and piezocaloric, it's the use of the combined properties. And then another parameter that is very important to take into account is the thermal expansion. Especially every material has its own thermal expansion. That means effectively the volume of the material will change in function of the temperature. And when you combine materials, I mean, when you have, for instance, a stack of different material, it's effectively mandatory to take into account of the different expansions of every material. So in this very huge family of functional oxide, you have a lot of crystalline structure. Along my career, I choose to work with the perovskite type structure, which is effectively the well-known formula AbO3. That means you need only two atoms, one big cation in the corner, we'll see after the structure, and one ion in the center of the structure, and the ion is surrounded by oxygen atom. In an oxide, effectively, you have also special structure, because we have grains. And if we talk about grain, between each grain, we have boundaries. So these boundaries are a special area in the material where you have crystalline discontinuities, and you have different properties, modified properties, due to this, I will say, inherent structure. We have effectively, it's not possible to realize and fabricate, I will say, a perfect material. It's not possible. So every kind of material include impurities, and these impurities will have effectively a huge effect on the properties. Structural defect. Structural means effectively in the crystalline structure, when we develop a material, we are far from the theoretical structure. Then we'll have a strong influence of the dynamics of ferroelectric or ferroic domains, because if we have effectively a special oxide with ferroelectric properties, these ferroelectric properties exist because we have domains. Here, ferroelectric domains. So on this slide, you can see this famous structure. So AbO3, designed here for effectively barium titanate. Here we are talking about barium titanate, which is one of the most studied material in the world. and it's already used in many applications. And the main interest of this famous biome titanate is its particularity is it doesn't contain any lead. So it's a lead-free material. Because another very famous ferroelectric and piezoelectric is the famous PZT. PZT means it contains lead, zirconium, and titanium. But the intensive, since a very long time, the intensive use of lead in many kinds of products and applications means effectively we have now real concerns about this lead, because lead can be found everywhere in this world, especially in all rivers, oceans, and seas. And now after that, these heavy metals can be found, in every fish or seafood. That's why we have in Europe since pretty, 20 years, we had effectively a special European directive for the restriction of hazardous substances. And that's why effectively since 20 years, there are so many studies on lead-free material, because it can be possible to find some similar properties without this dangerous lead. So in this perovskite structure, in the corner, we have the barium, the big cation. And in the center, we have titanium, which is a small anion. So we have different polarization, polarity between these ions. And around the anion, we have the famous oxygen octahedron. And this is here the perfect structure. After, when you develop your material, you will have some defects. That means sometimes you imagine this length, that means one side of the pseudo cube, in function of the different atoms you use in your oxide, but it's something close to 1 nanometer. So it's very, very small. And when you make, for instance, the seal films, in the base theoretical idea, you will superpose in 3 dimensions. You will addition some pseudo cube like that, in every direction to fabricate your material in the desired thickness. But of course, in practical, after experimentals, effectively, your material is not like that. It's very different from the theoretical structure. So that means the defects can be, you can have a lack of anions, of cation in the corner or here in the center. You can have some impurities that replace effectively the different ions, or you can have a lack of oxygen. That means the octahedron is not filled with oxygen. You have what we call oxygen vacancies. And these oxygen vacancies will influence especially the conductivity of the material. So here, on the right part, you have the different polarities of all the atoms you can find in the structure. And after that, in case of barium titanate, you have the different phase you can encounter when you study the material in a large temperature range. So at very low temperature, barium titanate is in the rhombohedral structure. And above that, it goes through effectively another phase, which is the orthorhombic phase. After that, above effectively the temperature related to orthorhombic state, the material came into the tetragonal structure. And you see the difference. All these three phases are ferroelectric phases. That means you will have an internal polarization with different direction in function of the phase, and this polarization will define all electrical properties. And when you go above the famous Curie temperature, so for barium titanate, it's something around 120 Celsius degrees, material becomes effectively a cubic material. That means in the cubic phase, this cube is really a perfect cube. That means all dimensions are similar, are equal. And of course, here it's an example for barium titanate. But if I dop this material, I will modify the different temperature related to the different phases. For another material, I will have, of course, different transitions, phase transitions. So defects, I talk about defects, and defects have very strong effects on all properties. The dynamics of these defects are influenced by local electric fields, domain boundaries, surface chemical potentials. That means you can have effects into the bulk and effects into surface. And finally, you combine all kinds of effects. So ferroelectric and ferroic properties are related to the bulk. Huh? You have effectively whatever finally the location of the domains. So in 3 dimensions, you have ferroelectric domains. But of course, here, when you talk about surface chemical potentials, you talk about catalytic activity. Here, it's mainly related to the surface. And this main, finally, properties is used for the development of, for instance, gas sensors. Yeah. So now I come to another definition, prediction. Prediction. What is prediction? It's the act of predicting. Predicting can be also stated differently. Forecasting, foretelling, prognostication, and the most well-known application of the forecast is for meteo. Yeah, that's why we have a lot of prediction for the weather, for the climate. Climate is studied for a longer time, of course. So the long period, short period, and of course, for all businesses, finally, these predictions are intensively used because for businessmen, have a careful look on sales and market trends. And all these predictions are related now to the use of AI, artificial intelligence. You have special algorithm, because if I have time, I will also talk about artificial intelligence, because all the studies and polls go into the same direction. That means the results of the different studies of population about AI. What does it mean for many people? Only 1 person on 4 or 5 persons can define quite correctly what is artificial intelligence. Everyone is knowing this word, but only 15 or 20% can approximately define it. So now, prediction for science, because here we are here for talking about science. We are scientists. We are not left out because effectively we have now a lot of powerful tools to develop our research. And here I am talking about finally the initial research before coming to the experimentals. It's now really interesting to have to use a prediction to compute some theoretical possibilities. And this theoretical computation, will also indicate to the researcher if he goes in the right direction. And finally, the main goal of the use of prediction in research will be to help researchers to avoid to waste too much time. Because if you want to try all solutions, you will need, in experimental, of course, you will need a lot of time. Yeah. But with the use of prediction, so with the use of very powerful computings, you can have effectively help for guiding you. That's the goal. But guiding is not effectively an insurance. In many cases, you can be guided effectively in a false direction. Yeah, don't forget this thing. So, I really like this picture, from this paper. It's not a young paper, recent paper, but it's really good because here you have a complete overview of what we can do in research. Here we have also research possibilities. And for the young scientists who are here in front of me today, you have all things in function of your main interest. You can do many things. So on the left part, you have the heart of the materials. That means the crystalline cell. So you are here in the lowest scale. You talk about atoms. You talk about angstrom. Because I said the dimensions of these crystalline cells are very, very small. Some angstrom to some tenths of angstroms. And when you go to the right side of this picture, you increase the scale. After that, if you develop a material with a defined thickness, you superpose all these unit cells in 3 dimensions to obtain a material which can be, as I said, in bulk, thick or thin film. If the material is in a ferroelectric phase, it will contain domains. And in function of temperature, the phase can shift from another one to another one. After that, if you have to work with very thin material, very thin material cannot be standalone materials. That's why the thin films must be deposited on a chosen substrate. And the substrate here has to be carefully chosen for the application. And then the last level is the device. The device in research in lab, when you want to go to the last level, the device, that means a lot of work and a lot of skills, a lot of equipment in the lab, because it's difficult to realize what we call also a demonstrator. With a device, you demonstrate really your final application and the final possibilities of your research. Of course, the device is also the first step before some possible extensions to industrial application. So that means that you students, you can choose to study different length scale from the atomic to the device. So many possibilities can be offered to students for their studies. So among effectively these different scales, we can study a lot of things. And the properties here are defined, like you can, with characterization, you can study the composition, the crystal structure, thermodynamic stability. You can use the transport, also you can study transport properties. You can also make some studies in function of temperature to study the phase transitions, phase diagrams. Can use also, you can study deeply the microstructure, because for the deep study of microstructure, you have, for instance, in your department, you have the famous SEM, scanning electron microscopy. And you can also study the domain properties, because you can observe also the switching of the different ferroelectric domains. That can be done with effectively SEM or TEM, for transmission electronic microscopy. For the last, effectively, a scale, you can use study the response to external field. Because, for instance, when if you want to develop an actuators, you will apply a high voltage, and you will measure finally the mechanical response. You can, after that, a very good thing to classify the performance of your material is to plot, what we call the figure of merit. And this figure of merit is also depending on the property you are studying. Yeah. After that, after theoretical or experimental study and characterizations, you have to make the correlation. And here, this is the job of real scientists and researchers, because you have to make it, to develop correlation between structure and properties, between microstructure and processing, between architecture for the device and performance. So you now fully understand that so many things at different scale can be done on each kind of material. And now I'm coming back to prediction. So I'm gonna present you some tools and some application to this prediction. So there are some software, dedicated software, powerful software that can be related to different way to study, finally, by computing. So we have the famous density functional theory. I will come back to that for one of our application. You have the molecular dynamics, the Monte Carlo computation, and finite element computation. They can be used to study effectively the effect of particle or domains, whatever the structure, in bulk on composite, but also on multi-layer structure. And they can be also used to compute effectively the theoretical response for ferroelectric, for instance. So it can be useful to study the evolution of the polarization for a ferroelectric, or for material dedicated to electrical energy storage. It can be useful to compute a theoretical response. Other application, a lot of application, in fact, because now this software are really powerful. And don't forget here that the full power can only be obtained if you have also the power of computing. Okay, if your computer is not enough powerful, you cannot do the calculations, of course. And all this calculation cannot be done with a simple notebook or computer, of course. I'm not talking about that. All these small computers are low power computers, and they cannot do the big calculation related to the studies I'm talking about. Yeah. So never forget that if you have an interest in computation, calculation, you will need a lot of power of calculation. And of course, that means huge computer, and huge computer mean also a lot of money, of course. Yeah. Because price of computer drastically increase with an exponential evolution in function of power, of the required power. Yeah. In term, you know that for numerical application, we are talking about effectively, for instance, because numerical computation means that you will effectively have as to define samples, numerical samples, and to have a defined number of samples per second. That means I'm talking about numerical rate. And the power is a function, finally, of that. So, in different papers, you have different application where you can study, simulation of domains, theoretic domains in ceramics. You can do it, of course, on films. And because I said previously that films will need to be deposited on a substrate, of course, you will have a strong effect of the substrate on the complete reaction, and you can study the mismatch with the substrate. Because we have in our oxide and other phase than effectively the paraelectric phase, where the polarization is killed, where the polarization is null. For other phases, of course, you can simulate the different evolution of the polarization. Other things important when you develop material, films or bulk. If I'm talking about, for instance, electricity storage. Electricity storage, it's a hot topic today. We need batteries, especially for e-vehicles, but also to store all what we call the alternative energy coming from mainly wind turbines and solar panels. It's alternative energy because, of course, by night, your solar panel, don't produce anything. No wind, no spinning of the wheel. Yeah, that's why the wind turbine don't produce anything. That's why where effectively some things like that, produce electricity, you have to store it, and this energy will be reutilized later. But to do that, you need to store it. You need very big unit storage. Yeah. Okay. So when you talk about finally storage of electricity, that means you will have to combine. As you know, you are physicists, so you know about voltage and current. Power, we talk about DC power. DC power means effectively you have only the voltage and the current. And you have to manage these two one because you have to get, you want to increase the power. That means you can increase the voltage level, you can increase the current level, or you can increase both of them. But it's not so easy. In particular, the most interesting solution is to increase the voltage. Why? Because when you transport electricity, if you transport a very high current, you will have also a lot of losses. Joule effect, you know it. You are physicists. The Joule effect, that means you transport electricity into your conductors. These conductors will be hidden effectively by the circulation of the current, of the electricity charges. This is effectively the Joule effect. Joule effect is, as you know, a relation between the resistance of the conductor, which transports the electricity, and the square of the current. So if you choose to increase the current, you have to really to take care about the thermal effect in your conductors for the transportation of the electricity. So that's why effectively the most evident parameters is to at first increase the voltage of your device. But to increase the voltage, you have to solve a big problem with the high voltage is the possibility to break down your material. We talk about effectively electrical breakdown. And you have to develop the resistance of your material. And here, that means your material should resist to be broken by the maximum applied electric field, resulted in the application of high voltage. When you have a breakdown, your material is destroyed. It's not a reversal process. If you have a breakdown somewhere, it's finished. The equipment, your material is destroyed. So that's why effectively computation can be done to study the effect of the structure or composition to resist to this breakdown. After that, you can have also some simulation for the distribution of stress. Stress is also very important when you have a different kind of application, like thermoelastic effectively application or piezoelectric applications. Then you have also, this is especially interesting for multi-layer structure. You can study the electric field distribution because of if you have multi-layer structure in function of the resistivity of each material, you will have effectively a special distribution of the electrical field. That's why it's very important to simulate this kind of effect. So this is the application of also the possibility of breakdown on a multi-layered structure. So many things can be done now by computation. But computation is really requiring special skills from researcher and scientists. If you want to be very performant in this way of study, you have to dedicate effectively your career to this special field of research. Because it's very difficult to efficiently use all this very powerful software. So, yeah, I was there. So now another study effectively can be done because I talk about ceramics, which are crystalline material. Of course, this computation can be done also for composites. Because in a composite, here you have to clarify your mind on that, you know. Generally, when you work with composites, that means you have a polymer structure, polymer matrix, and you will add some particles, and generally, you will have an interest to put some crystalline particles. And here I'm talking about powder, crystalline powder. And in every case, when you put some oxides powder, you know, in a matrix polymer, you will obtain this one, this structure. And as you see, effectively, the problem is that you have a concentration of your oxide particles. And that means that you will obtain non-uniform properties of your material. And then the goal for all researchers who work on composite, nanocomposite, is to obtain this final structure where all the particles are quite regularly, you know, distributed, you know, into the matrix structure. In this case, you will have quite uniform response. So then, for nanocomposite, you know, finally, this computation can also be done in function of different materials because in case of also multi-layer, you can have some different distribution of the material as well. And this different multi-layer structure can be also computed for composites. Another application is very interesting to be studied by prediction is when you mix different families of material. And recently, there is also a huge and intense, you know, activity of the researcher about the study of mixed materials, mixed oxide between ferroelectric oxide and ferrite. And when you mix this kind of material, you can have different case because you will tune finally the percentage of each material in your final structure. And simulation can be very efficient to predict the properties of your material and, of course, the trouble you can be able to observe later by experimental. So here, simulation were done, you know, with a different percentage of the ferrite. Here you have 10, 30, 50, and 70% of ferrite. Of course, if you put ferrite somewhere, it's because you have an interest in magnetic properties. It's for the development of magnetic material. Magnetic material has also a huge, effectively, evolution because you have many applications for actuators, motors, and so on. Also, of course, for a transformer, I'm talking about power transformer. That's why, effectively, it's interesting also to simulate and compute the different rate of mixing you can have, you know, as this kind of association to try to obtain the structure and the properties you expect to have. Because, of course, there is always a difference between the theoretical study, the computation, and then the experimental results. Yeah. So the goal for a researcher is to try to obtain finally a material as close as possible than effectively the material that would study under computation. And that's not easy. So for scientists who work in electrical engineering, there are already a lot of software. So I'm also have a slide to just discuss about the tool which are available now. Of course, everyone is knowing about MATLAB, which can include effectively Simulink. For simulation in electronic application, you have effectively, for instance, because there are many software, PSPICE, multi-sims, and so on, and other for different application, for power application, for instrumentation, effectively, National Instrument also provide this famous software, LabVIEW, which has numerous application in industry. And in physics, another very powerful tool is COMSOL multiphysics. And it's really a very powerful software and very difficult to use. Because you can need effectively to work on it for some years to be able to use the full options. And this software is really used in everything. It's used for electrical application, but also for automotive applications or for optical application. And every domain you can make this application. But here, of course, from these figures, you understand that you have simulation generally for devices. Yeah. If you simulate, the structure of an exhaust system, or if you simulate effectively a structure for optical fibers, you are directly connected to application. So now I'm gonna move to effectively one of my applications for electrical energy storage. And this was a study of, a perovskite structure. So it's STO, strontium titanate, where we doped, so we exchange a part of the strontium by calcium. So why do we do that? I'm talking about electrical energy storage, EES. The Ragon plot is a useful plot, to understand the different devices that we have now in your common life. And this plot, we have got two axes. So axis is energy density. You see the unit. Energy density, you have, this power, this energy, watt-hour per kilogram. That means you have directly a connection between the energy, electrical energy, and the required mass of your device. And in the y-axis, effectively, you have the power density. Power is only power watt per kilogram. So these two main, effectively, two main properties to characterize these devices dedicated to storage. And you have all the formulas. Currently, so batteries, Conventional mean electrostatic capacitors. And in the middle, you have supercapacitors, which is a special technology. Which is very different from conventional capacitors. Conventional capacitors, you have two electrodes. That's all for every capacitors. In batteries, you have effectively anode, cathode, and electrolytes. And it's quite similar effectively for these capacitors. So here, in my study, we're interested in high power capacitors, electrostatic high power electrostatic capacitors. And I move back to this famous effective and well-known cycle, the ferroelectric cycle, also called PE loop, polarization in function of electrical field. And here on this figure, you have the classical ferroelectric shape in red. This is the common response of a ferroelectric material. When you want to develop a memory, so when you want to store an information, means you store a numerical information, 0, 1. In this way, we are linked to our memories on our computer. You need to have this shape for the cycle because in absence of electric field, you need to store the information by using effectively the remnant polarization. Because your computer, when you shut down the computer, informations of course, in some kinds of memories are still all in the memories. You don't lose effectively your work. So after that, it's very different when you talk about energy storage, because here you talk about electricity storage. For electricity storage, you have only an interest not in the red area, but in the green area. That's why when you want to develop a device for electricity storage, you have to decrease the red area and to increase the green one. In our world, we have 3 kinds of families. We have pure dielectrics, which are always in ferroelectric state. We have ferroelectrics with this famous cycle. This is the imprint of ferroelectricity, but the possibility of storage is low. That's why effectively it's not possible to use ferroelectrics for energy storage. Then you have the antiferroelectrics with a double cycle. Here, this is also the imprint of antiferroelectrics. Problem with this family is that in this world, we have very, very, very few material which present this famous antiferroelectric cycle. And most part of them are lead materials. So they contain lead. That's why I don't work with this family, because I dedicated during all my career, I dedicated all my studies to lead-free materials. So currently, I mainly work with effectively relaxers, which present a very important area for storage. And of course, you can combine the dielectric behavior with relaxor behavior. This is my new trend, for my new studies. So there's parameters you need for electrical energy storage: high electric permittivity, low dielectric losses, high saturation polarization. So I repeat, high saturation with very low remnant polarization. So very low, low coercive field, and then high electric field, maximum electric field, because the value, the possibility to store will be a possibility to increase the voltage applied to the materials and then to the device. But we have to get in mind that it's only possible to increase this famous highest electric field only if our material is possible to resist to break down. Because in the other way, when you will increase, and when we study, when we study the limit of this kind of material, in practical, we see it. You see, we see the breakdown directly, because we observe in the material, of course, a small thunder. You broke your material, electrically broke. So this is the first attempt we done with this material. It was in 2018 with one of my master students. And at this time, I saw that it was very interesting to work around this doping rate with a maximum of 40% of calcium. Because even if we decrease effectively the dielectric constant, we saw that it was really possible to decrease the losses. And even if these response were not ideals, because, of course, we didn't at this time optimize the ceramic, it was really a very interesting preliminary result. And during another thesis, more recent, I worked with very good PhD students from India, and we studied, this material in a more defined, structure. We studied everything from the theoretical point of view up to effectively all different material forms. And I will here present you the theoretical studies. So from the diffraction made on powders, we made Rietveld refinement. Rietveld refinement is really very interesting. So you need also a dedicated software. And every time you need the complete software, because this kind of software, you have different, not many, but some of them, you have different options. And every time for every option, you have to pay additional money. So with this refinement, it's really interesting because you will make a full characterization of the solid state material, starting from the diffraction, X-ray diffraction. And then by computation, it's possible to calculate, the diffraction pattern from a crystal structure. So you can superpose the experimental diffraction to the theoretical diffraction. So computed model. So that's what we've done for effectively some material. I don't present everything here because here I present only two doping rate, but we've done for different things because at this time we were interested in the possibility to have a special tilt in the structure for optimization of the behavior, the ferroelectric, and here it's not ferroelectric, it's we thought that effectively in some particular composition, we could find in local places, we could find something close to an antiferroelectric function. So all the theoretical studies was done, and by effectively studying some specific peaks, we studied and we showed that an antiferroelectric lattice peaks were observed, of course, in the 2 theta expansion at different angles. And that was for us a very interesting track to follow, because this possible existence could modify completely the behavior of our material to increase the storage performance. And with effectively additional options here, Vesta, it's also possible to materialize finally your structure in function here of the doping, because our initial structure was strontium titanate. We included inside, by exchanging effectively a part of strontium, we included different rate of calcium. So we are between the pure strontium titanate and the pure calcium titanate. And here we revealed theoretically that with a particular percentage, it could be possible to really roughly modify the structure for having finally a possible antiferroelectric phase. And that was revealed only with effectively this theoretical study made by simulation. So in this first part, effectively, I'll talk about the intensive use of field analysis with full option pack. And we've shown the possibility of the existence of local antiferroelectric behavior. And then I will move to effectively the experimental way in the next step, because, of course, every time you use software, every time you compute on a structure, you don't include in computing all real parameters, like effectively the fact that our crystal, our material, is not only composed of perfect crystalline cells. All these cells include defects. And I defined previously in my talk, all kinds of defects. And so real films have many defects. And at this time, there is no tool to simulate them. In future, effectively, by increasing the computing power, it could be surely possible to obtain something more efficient, which includes the possibility to define is the input, of the algorithm, to define some particular defects. But at this time, it's not possible to do it. And when you work, on material and dedicated to storage capacitors here, you will get the truth only by studying the PE loops, because the PE loops is giving you all values for the energy storage. And of course, P loop is also the way to observe the response of your material. So another part is dedicated to thin films. What it can be done to thin films. With another of my students, I studied, another perovskite because since 15 years, there is more and more studies on the possible use of perovskite structures or perovskite oxide for solar cells. And if you have a look also on Google Scholar, and you type effectively perovskite solar cells, you will see that effectively there is more and more publication on this topic. And in future, that will increase more. So here, I chose this material because it was not an expensive material to realize, and it's possible with the properties of this, because here, it's a perovskite with barium in the corner of the cell, in the center, yeah, we have tin, which is also not expensive. So it's really important when you develop something to try to find some and to choose some material which are not very expensive, because you can choose to do it, but after that, when you have something in your lab with expensive material, and if the results are interesting, the difficulty will be to move to the upper scale of application. And that's also a very important condition if you're interested to develop applications. Because application, when you talk to industrial partner about application, directly, the main question they will ask you will be, okay, Prof, a very good material. How much? How much money does it cost? If I want to design effectively 1 square meter of solar panels with this material, what will be the cost of the panel? So you make the calculation, and if effectively you say, yes, my panel will be 10,000 USD, your possible industrial partner will run away very quickly. You say? Because currently, the price, for solar panels made with silicon. And at this time, we didn't invent new solution to produce effectively cost-effective solar panels with another technology than silicon. So here we use another very powerful tool for the theoretical study. It's I'm talking about family of ab initio calculations. Ab initio calculations are related to the microscopic structure, and we use density functional theory. For calculation, you have to choose tools and to define many parameters. Here, you have some of these basic parameters. This is the package we use for calculation. We define some approximation because for every calculation, you have also to define hypothesis. And then here, this is currently released the weakness of calculation with the power of calculation we used at this time, it was only possible for us to make this calculation on a very small volume. On each dimension, x-axis, it was only possible to define effectively two cells on every direction. That means we made the calculation on a big cube, which was double of one cube, but not more. And of course, you directly have to switch here for saying, oh, yes, we'll make the calculation, but we'll be far from the real structure. Because even a thin film of some tenths of nanometer will be, of course, in the large superscale higher than this atomic references. But for increasing and to be more in touch with better result, I would say, by calculation, you have to increase the number of cells used for simulation, but at this time it wasn't possible for us because it should have been necessary to use a super calculator, and we didn't have the access to this kind of equipment. But nevertheless, computing is interesting because it shows you the possible interest of some doping. Is that what we do? We see here for this variant material, we doped it, by cobalt. And simulation is also limited the way you choose to choose a doping rate. So here it was only possible, to choose for 12.5, 25, 37.5, and 50% of cobalt. But you will see that nevertheless that was interesting. So DFT is a good tool because here you can dedicate the studies to the study of electronic properties. Our material, perovskite structure, have, of course, we said it, we are talking about semiconductors. Semiconductors mean, for physicians, something should be known because we talk about semiconductors. Semiconductors are between full metals and insulators. When you have semiconductor, you have a gap between the conduction band and the valence band. This gap is really characterizing your semiconductor. And the goal, you have to keep in mind the reference. You have to keep in mind the reference. Reference for them is silicon. The gap of silicon is interesting because it's below 1 electron-volt. And this is the goal, to have obtained, to be able to fabricate a new material with a very low gap of energy. So when you make the simulation, of course, you verify the possible gap of your material between the different electronic bands. That's what we've done with this material for different level of cobalt. And here you have the result of simulation, A, B, C, D. So A, B, C, and D for the different percentage of cobalt. And what we've seen that we have a reduction of the gap. So good thing. What's good? Because a classical perovskite semiconductor, as generally for all kind, because we have large family, we have a gap from 2 to 3 electron volt. So of course, in this way, it's too high, for solar application. But we saw that effectively by increasing the doping rate by cobalt, we decreased finally this gap. This gap is, you see, the red arrow defining the gap between the two electronic bands. So by increasing doping, you see the size of the arrow, so size of the gap was decreased. And here's the result. We plot the evolution of the gap without doping, so 2.6 electron volt. With 50%, we decreased to 1.4. So that wasn't bad because effectively that was a large decrease of the gap. That's why we performed. And we go to the next step, which was effectively the experimental applications. But before that, of course, I show you some extended application you can do with DFT tools. I show the possibility to completely study the electronic structures, electronic properties. But here, you can also study the effect of the different, the effect of the doping on the different bondings existing between all atoms of the crystalline cells. And that was interesting because here we showed that covalent bond between tin and oxygen is gradually weakening upon an increasing in cobalt doping, and then that cobalt is forming covalent bonding with oxygen atom. That's why these two remarks, were the synthesis finally of this effect. So why do we decrease effectively the energy gap? Because we have these two effects. So in conclusion, I will say that DFT is also a very powerful tool for predicting electronic and optical applications, because it can be dedicated to optical properties as well. For semiconductor, and here we had made the prediction that cobalt could effectively decrease the gap, and theoretically that was effective. And after that, I always say to young physicians and scientists, take care, don't forget, effectively. Here, with DFT, we only work with some cells. So the model was restricted. It wasn't possible to have a larger model with an increased number of cells because that requires a lot of computing power. After that, effectively, we verify the properties by experimental. We effectively deposited thin films with salt gel technique and spinning of the solvent of the solution on substrate by using spin coating technique. And then effectively we have done it. That's not in progress, that was done and published. So thank you for your attention. After a short break, I will start my next presentation dedicated to other materials.
Thank you, Professor Didier, for your presentations. Now, okay, please give applause to Professor Didier. Now we are going to next session for a Q&A session. Do you have any questions?
Only to our question, even a private question, basics.
Yes.
Okay.
Di online ada yang nanya.
If
Okay.
Sure. Okay. Thank you for the opportunity. Good afternoon, Professor. Actually, I was late coming to your talk because, yeah, I have some errands to do. My name is Nisa, Professor. Uh, yeah, I work with some oxide, especially not semiconductor, but I work with a transition metal oxide. Yeah, like titanium oxide or magnesium oxide, tungsten oxide, and etc. But I don't specifically work with semiconductor. But it's like I work in how to um, elaborate the surface properties of the oxide, like for optical properties or some structural properties, something like that. So I have questions regarding the modeling or the prediction of the structural properties by the FT, Professor. Uh, Actually, I didn't see your slides in the beginning, but what I get is we can predict the optical properties by means of density of state data, right? Like DOS, and then we can see the location of the valence band, right, Professor? How about the structural properties we can predict by DFT? What kind of parameter we can estimate from DFT, Professor?
Currently, this is the researcher who must choose finally the material. For in my example, I talk about the doping by cobalt,
Yeah.
and we choose it because if at this time there is no enough efficient tool to also effectively compare the possible effect of doping by different material.
Mm.
Uh, it will be surely possible in future with the development of AI,
Mm-hmm.
but at this time there's nothing.
Mm.
The choice of evolution of your material is the choice of the researcher currently. But the predictive tools are interesting because they can guide you. They can give you some interesting information because that's what I said previously. This information are far from the real properties, but nevertheless, there, this is the software, the computation give you a trend. It will also indicate you if your hypothesis is something interesting or completely bad. For instance, in my previous presentation, we wanted with my student to develop new material for solar panels.
Yeah.
We need semiconductor, of course. So first choice, it's only possible to work with semiconductors. Yeah. Then you have to choose a structure for this semiconductor. Here I chose, of course, to work with the perovskite structure because that was also one line I followed during my career. Because you can do many things with this family, because possible to dope the material on each side.
Yeah.
So, and then with computation, we make also the choice to try to compute the effect of cobalt.
Mm.
So the first work of a young researcher, if you want to start with this kind of study, is to have sufficient background, and sufficient background, you will obtain it, by an intensive study of literature, to be able to at first define different possible dopant you can use in your structure. And after that, you compute them. I show you the computing results, and here the results were quite interesting because the result indicated us that cobalt could be very interesting because actually, effectively, doping decreased the energy gap. And that was what we wanted. To come closer to the silicon functioning, we need, it's a full requirement, we need to decrease the energy gap. Okay?
So, Professor, so actually, the structural properties that we can estimate, does it something like the strong bonding, for example,
Of course.
between the
Yeah.
cobalt and the parent, for example?
Yes.
So we can estimate. So if I have, for example, the parent sample is for example, cobalt oxide, and then I want to add some other oxide, for example, titanium oxide or manganese oxide,
Yeah.
and then can we estimate the adsorption behavior between manganese oxide comparing to the other oxide to the parent oxide, which is the cobalt oxide? Is that what you mean by structural properties, Professor?
Yeah, because the DFT calculation will give you, all
The
electronic
energy, right? And yeah,
computation
I mean
on
beside
the
the
electronic
electronic,
and
yeah.
also you will have also finally directly optical properties.
Yeah.
It's also possible to have them.
Okay. Yeah.
Because it's really something you have in parallel, electronic and optical properties. It's neighbors, because what is finally here for solar panels, I'm talking about photovoltaic reaction.
Yeah. So
That means it's an optical because you use light. You convert effectively photons, which are injected into your structure, into electrons.
Right. So we can estimate each bond, even atoms between atom, right, Professor?
Yes,
Interatomic distance.
You evaluate effectively bondings in your
So
structure.
Okay, thank you, Professor. So if we have, for example, organic structure or polymer, which is very complex, right? The structure. Can we also estimate the adsorption
Organic
energy?
could be more difficult because most part of organics are not crystalline.
Yeah, right.
That's why it's more difficult in this way. And as I said, when I talk about composite, because even for organics, the trend now is to mix organics with sometimes oxide powder. And it's very difficult finally to, in this way, to obtain, I will say it, an homogeneous structure finally of your samples, because you want to position different particles very regularly into your organic material. And it's very difficult because here you have also to manage the interaction between the material matrix and interaction between the different particles you inject in your material. And here I'm talking about electrostatic effect.
Interaction, yeah,
Yeah,
electrostatic
interaction.
interaction. So we can say that maybe DFT is it DFT is limited to some crystalline structure materials only, or we can
But
actually
this time, I never work on effectively. I only work with some polymers, and these polymers were ferroelectric polymers.
mm,
Uh, so I never work with effectively real organic materials. But the difficulty is that is because your organics matrix is definitely not crystalline.
that's make it's
And
not easy to estimate by
and
the FT,
simulation
right? So
currently can only be done
on crystalline materials.
on well-known structure because what is the crystal?
Mm,
Crystalline structure are organized structure.
I
Cell.
see. I see. So
It's not. It's with organic structure we are
mm,
far from that bit.
mm,
It's an organic structure is completely amorphous.
yeah, completely amorphous.
That's why
I see.
you can simulate, I guess, but not by DFT.
I see.
With other tool, you can. I guess it's mainly because final properties of this kind of composite between crystalline and organics. Many studies there are an interaction on this topic,
But not with the FT, right, Professor? Maybe, yeah.
but simulation. There are some tools to simulate the effect of this inclusion of particles. There are because they are based on effectively simulation of the interaction of particles, but only it's only electrostatic interaction
Interaction, yeah.
because there is no electronic properties on organics.
Mm.
And another problem with organics um, because it's not we are organics, but we have a long lifetime because we are we are self energy production systems.
Yeah, so we don't
So for
use the
organics,
organics, yeah.
when you work with organics, you know, in the lab, currently and since 20 years, the main difficulty is the lifetime of your
Materials,
sample.
yeah, yeah.
And
I
this
see.
is really difficult, even if you in the first hour of study, you show some very interesting properties. The problem is effectively this effect will only be stable for some days. Sometimes the best weight will be stable for some months,
Yeah,
but it won't be possible to develop an application, you know, for long duration.
yeah, surely.
Yeah.
Yeah, surely. Okay, so there is some limitation for this functional theory to simulate or to estimate some organic structure, right, Professor?
No,
I,
DFT at this time, you know, it's for crystalline.
yeah,
Yeah.
yeah. Okay. Thank you so much, Professor, for your
You're
answers.
welcome.
Any other questions from online participants?
Yeah. What? How many?
Can we close now?
Oh, yes. Also. Okay.
Thank you so much. Okay, because we have a limited time, so we have to end the presentation from Professor Didier Fasquelle. Please give applause to him. Thank you so much, Professor Fasquelle, for giving a public lecture. Now, Pak Budi will give the okay for Professor Didier Fasquelle. Certificate and also souvenir. So the participant, would you like to yes to have a part together? Ayo semuanya join.